Welcome to the next episode of the YugabyteDB Friday Tech Talks series. This is for engineers, from engineers. And I'm Kannan. I have with me today R.K.N. Sai Kumar, Sai Krishna, if I'm, I think I got your last name, but he goes by R.K.N. So I'll welcome R.K.N. Love for you to introduce yourself and also the topic for today. So why don't we get started?
Sure. Hi all. This is R.K.N. From Yugabyte, a part of database team in India. So prior to Yugabyte, I worked for Teradata and Microsoft. Throughout my career, most of the time I have spent in database space. So let me start by sharing my screen. I hope my screen is visible now, right?
Yes, R.K.N.
Yeah. Thanks. So today I'm here to talk about some of the CDC enhancements that we have done in Yugabyte. So the agenda of my talk is I'll just start with a quick introduction to CDC, change data capture, and then some of the recent enhancements that we have done. They are before image support, and then how CDC takes care of schema evolution, which is in more which was asked by customers, so many customers, and then dynamic addition of tables. So how we start streaming changes corresponding to the tables that are added dynamically, and then tablet split. And towards the end, I'll have a short demo showing the behavior of CDC with all of these features in. Right. And before image, schema evolution, and dynamic addition of tables, these features are already available in 2.16 release. And before image is going GA in 2.18.
And when you say available in 2.16, so it's more of a preview feature in that release, and the GA will be in 2.18. Is that the expectation?
Yes, yes.
And what about the last bullet, like the tablet split?
Tablet split is, I'm sorry, before image, schema evolution, and dynamic addition of tables are already available, and tablet split is going to be beta in 2.18.
Got it. So that is still in the work. It's not generally available, the tablet split.
Yes.
Support with change data capture. Got it.
Right, right.
Thank you.
Right. So let us start with change data capture introduction, right? So in short, CDC. What is CDC? CDC is a process of identifying and tracking the changes that are made to the data in Yugabyte. And it provides near real-time updates for analytical and other use cases. And it also helps maintain consistency across all of the systems that are relying on this part of the data. So let us quickly talk about some of the use cases, right? Again, I just showed very few use cases here. There are so many use cases of CDC. So let us talk about some of them. The first one is data replication. So CDC can be used to replicate data to multiple other databases, data lakes, data warehouses, to ensure that they have the latest version of the data, right? And similarly, we can consider a mobile app which is modifying data in a table in Yugabyte at a very high rate, right? Let us say some thousands of updates per second. And in parallel, another application could use CDC to capture and store the changes, store the data about these updates, and provide some real-time metrics for the mobile app. And another application could be, a financial application modifying stock market data in a Yugabyte table, and multiple other applications running in parallel could use CDC and rebalance the portfolio based on the stock price movements. Again, these are only some of the use cases that I have listed. There are wide varieties of use cases for CDC. So let us now look at the CDC pipeline in general in Yugabyte, right? So an application or an entity would come and modify data in Yugabyte tables, and the intention is those changes should be streamed across to and written to Kafka topics. So that based on the use case, the data, change data would be read from the appropriate Kafka topics and further processed. So to achieve this, we have a Debezium connector for Yugabyte in the middle, which is pulling in all of the changes that are happening in Yugabyte and then streaming those and writing to appropriate Kafka topics, right? So to enable CDC or to start streaming, today we need to create a change data stream. And by default, the granularity for creating the stream is at a database level granularity. So we create a change data stream at database level. So when we say we are creating a change data stream for a particular database, there is no necessity that, we force people to stream all of the changes corresponding to all of the tables within the database. So there is an option in the Debezium connector to have some include list, so that we stream only the changes that are happening on specific tables, and we stream changes corresponding to the updates or writes that are happening on only those subset of tables. And the changes, another point to note is the changes are streamed per tablet in Yugabyte. So most of you must be aware that a table's data is partitioned in Yugabyte and then distributed across. So we call each partition as tablet in Yugabyte terminology. So we stream the changes per tablet. So with this context, let us talk about the before image support first, right? So let us see the change records or the CDC records prior to the before image feature was introduced. So let us understand that with an example. So let us say I'm creating a table, an employee table with just a couple of columns, a simple table just to understand it better, right? So an employee ID and employee name are two columns within the employee table, and we just insert a row followed by an update and deletion of the same row. So if we look at the CDC records corresponding to update and delete. Again, what I have pasted here as CDC record is only a small snippet of the actual CDC record that would be shown up in the Kafka topic, right? Whatever is needed for our discussion, I just picked that snippet, right? So it will have two sections, the before section and after section. And prior to before image, the before section would be null, and after section would have primary key column, primary key, which is employee ID here. So we have employee ID and the corresponding data associated with it. And then we have the modified columns with the appropriate data. Rest of them would be populated as null in case we have other columns. In this case, we just have two columns, right? And when it comes to delete, we just show up in the before section, we just show the primary key, and rest of the non-primary key columns would show up as null. And of course, after section would be null, because after section talks about the current image, post applying the operation update or delete, what is the current row image, right? So that obviously would be null. After applying the deletion, we don't have any row. So this is how the change records look like for update and delete operations prior to before image came into existence. With before image, continuing the same example, right? If you look at the CDC record for update, we will have in the before section, we will have the image of the row prior to the operation, the update operation taking place. So in this case, whatever was the row image that we had at the time of insert, that would be there in the before section, and after section would have the row image after the after applying the operation. And in the case of delete, we populate the entire before image of the row prior to the actual deletion of the row, right? So this is what it looks like.
So
now, yeah.
R.K.N, one minor question. I mean, something I noticed in the previous slide.
Sure.
You see the integer value for employee ID is shown as value and 1001. But for string, there seems to be another level of like nesting. It says value and then string and then Alice. So is there just a special handling for integer types versus string?
Yeah. So we show up different data types. So in this case, basically we do not have under value another section and so on, because that's just the primary key. But for rest of the columns, I think I have an example which shows that, right? So under the value section, we show what is the type. So either integer or character or string or whatever. So under the value section will show up the string.
What is the reason for the difference between the primary key portion of this versus the non-key columns?
It is just the pattern that is followed in creating the record. There is no one specific reason that we create in this particular manner, but otherwise we populate for all of the non-primary key columns. We just populate the value section with the appropriate data type also showing up along with the value.
Got it.
Yeah. Right. So just continuing on the before image, right? So what exactly is a before image? Before image is the state of the row before the change event has occurred. Whatever is the row version that was existing prior to the change event occurring. So this will be populated for update and delete events. For insert, obviously, it doesn't make any sense to create any before image because we are just introducing a row version. There are no versions prior to the insert. So, and in Yugabyte, so basically Yugabyte storage layer is based on LSM tree, right? So none of the write operations that we do are in place, right? Which means that, when we perform update operations or write operations on a row, the same row is not updated again and again as part of a write operation. Rather, we create multiple versions. So for each write operation, we create a version of the row, right? So we retain the older version, we retain the latest version, and then usually we garbage collect. So the older row versions are what we refer to as history. So by default, we retain the history for 15 minutes. So last 15 minutes of history is always retained by default in Yugabyte. So just to elaborate a bit more, so if we say the current time is T, so we retain all of the row versions starting from T minus 15. Prior to that, we garbage collect all of them. Or, in our storage terminology, we go and do the compaction process for all of the older rows prior to 15 minutes, right? So that is what is the default behavior. Now with before image, with the support of before image coming into picture, we need to retain. So what we are saying is at the time of streaming a particular row, we stream the current version of the row, and we also stream the previous version of the row as part of the before image, right? So we always need to have the current version that is being streamed and also the previous version that is needed for the before image. So we modify the retention logic a bit to make sure that we have the needed before image or the before row version that is available, so that we can create the before and after sections appropriately in the change record, right? And another point that we also need to talk about is, when multiple CDC streams are created, then some of the streams could be up to date, some of them could be lagging a bit, right? So in that case, to make sure that even the most lagging stream streams the before image successfully, the retention logic is modified, keeping the most lagging stream in mind, so that we successfully stream the current change record and also the before image associated with it. And with this, it's obvious that if a stream is lagging, we end up storing more data, right? That is one side effect of this before image feature. In addition, what we also do is we identify the garbage and also garbage collect the older row versions which are no more needed. So across the CDC streams that are created, if there are row versions which are no more needed, we identify those and garbage collect behind the scenes, right? Another point to note here is when we are creating a CDC stream, when we are streaming a particular record, we use the schema that is associated with the write operation. That is, we use the schema that is associated with the write operation for which we are creating the CDC record. So the stream, that particular schema would be used for populating the before and after sections at the time of creating the CDC record. So how to enable the before image feature? So when we are today to stream the records, we create a change data stream, right? At the time of creating the stream, we have this additional option created of record type, which says all. When we say all, it says that we are interested in streaming all of the changes, including the before and the current row images. So That's pretty much it about before image. So let us now next talk about schema evolution, right? So what is the problem that we have with schema evolution? So let us consider one example here to talk about schema evolution and the nuances associated with it, right? So let us say I created the same employee table again with schema version, which initially has a schema version 0, and then I inserted a row followed by and altering the table results in schema version 1. And subsequently, let us say we are updating the previously inserted row, and then we now modify the table again. We alter the table, which results in schema version 2. Now, if you see, the latest schema version of this table is 2, and then let us consider that let us consider one CDC stream which is a bit lagging, right? And it is streaming the record. It is creating a record corresponding to update. It is just populating the CDC record. So the schema version associated with the update is schema version 1. And if we want to populate the before image as well, right? In this case, the before image is the row version that was created with insert, right? Which is for which the schema version, associated schema version is 0, right? So now when we want to create the change record, we cannot use the latest schema. We need the correct schema, appropriate schema to decode the column values and populate the change record correctly, right? So in this case, we also need to make sure that all the older needed schema versions are there available to, to decode the column values correctly and then frame the CDC record. So if you see, if we can, if we are successful in retaining the schema, all the needed schema versions, then we see the CDC record that would be populated appropriately on the right side. So if you see, we populate the CDC record using schema version 1. And as I said earlier, before image also uses the schema associated with the with the record for which we are creating the associated with the write operation, right? In this case, the write operation is update and the associated schema version is 1. So we use schema version 1 to populate the before and after sections. And that's why we see, even though department ID was never existing when we inserted the row, we still populate that with a null value, right? And then appropriate department ID and the corresponding values here.
R.K.N, just to make sure,
yeah,
we are saying that this schema, like some CDC stream is lagging and it is creating this CDC record when the schema version is already at 2, but it is intelligent enough to work with the schema version 1 because that is the corresponding version at the time the record was updated, correct?
Exactly. Yes.
Okay.
Yes. Yeah, I think these are some of the pain points for which, many databases face a challenge in supporting the schema evolution. Right.
Makes sense.
So, yeah. So now let us talk a bit about schema evolution support, right? Once now we understand what exactly is the problem. So we need to have the older schemas handy, keeping in mind all of the lagging CDC streams so that we can create the change records correctly. And we need to have the corresponding schema version for creating the change record. And at the same time, we cannot go on storing all of the older schemas. So if there are, if a particular table is being altered altered frequently, then we cannot store all of the older schema versions. Our interest is to keep only the needed schema versions and garbage collect the older schemas, which are no more needed. And as discussed, if we have before image as well enabled, then we also need to have the schema version associated with the before image as well to decode the before image correctly and then populate in the change record. On a side note, we stream the DDL records as and when they happen, as and when a table is altered in Yugabyte, and the connector is always aware of the current schema version for which the associated change records are coming in. So that's about schema evolution. Now, what is it about supporting dynamic addition of tables? So let us say we created a change stream on a database, right? As we discussed, we created a database level. Now, after creating the database, it is a very common practice that new tables are created within that. And, as we also discussed, we could have table inclusion list, and most of the times it could be a regex saying star, I want to stream all of the tables. Now, if new tables are added, we did not want any manual intervention or any other configuration changes, etc., or new streams to be created to stream the new tables that are introduced within the same database. So the server also takes care through this feature to add all of the tables to the stream. So the connector as well as the server takes care of this by having additional logic to include this table as well to the stream, and we can seamlessly stream the changes that are happening on this newly added tables as well. So that's about dynamic addition of tables. I think we can see how it happens and what is the behavior in the short demo in a while. Now, what is it with what is the behavior of CDC with tablet split? When I say tablet split, the partition is further being split into two and so on, right? So again, let us consider an example to understand it better. So for example, we are creating the employee table and then inserting a row into the parent tablet. That is, when I say parent tablet, that's the original tablet prior to the tablet split. And then let us say, I'm sorry, a tablet split has occurred. And then say subsequently, I'm just inserting couple more rows, which are going into two different tablets. So in this scenario, multiple things to observe here, right? One is if there is a CDC stream which is still streaming the changes corresponding to the write operations that happened on the parent tablet, even though a tablet split has occurred, right? In that scenario, we need to keep the parent tablet alive, or we need to retain the parent tablet so that we can successfully stream all of the changes that happened on the parent tablet. And then after the child tablets, even though the child tablets are created, we should again make it so graceful that there should not be any other things to be taken care to make sure that we can successfully stream all of the changes that are happening on the child tablets too, post tablet split, right? So if we can take care of these things, then we can successfully stream the change records to the Kafka topic, even though there is a tablet split. So that with the tablet split support with CDC, we achieve this without any downtime or without any need for creating new tablets. Again, new stream, I meant, right? Creating a new stream and then polling on these new tablets again. So what is a tablet split? It's an existing tablet that is split into two because the parent tablet is growing bigger and bigger. And I mean, this is just one reason. There could be many other reasons because of which tablet split can occur. And new tablets, the newly created tablets, when I say newly created tablets, the child tablets, if we take the previous slide example, right? The child tablets will be automatically registered on the server, even though there is a tablet split. And connector need not be informed as soon as a tablet split occurs on the server, right? Because there is no need for it to know. So if it is streaming changes prior to the tablet split, it just moves on, and only when tablet split op is seen in the change record or in the change history, the connector will be informed appropriately. And as we also discussed, parent tablet needs to be retained as long as there is an active CDC stream that is polling it. So that's all I have about all of these 4 features. So now let us quickly have a look at the demo. So what I will be covering in the demo is I'll just explain the setup steps. So what are the steps that are involved in setting up the CDC pipeline? And then after creating some set of tables, and then after some write operations, how the CDC records look like in Kafka topics. And then I will move ahead by adding a table dynamically to the existing stream, and then show how the change records are being streamed, and wherein we also see how the before image is populated, how it looks like, and so on. And then I will alter the table, basically demoing the part of Schema Evolution. I'll just modify one of the existing tables, pre-created tables, by adding a column and then performing the writes, and how seamlessly all of those show up in the Kafka topic. And towards the end, I will split up a tablet manually and then show that it is, CDC takes care of it gracefully, right? So that is about the demo. Now let us move to the demo part. So we have something called CDC examples, a Git repository, which talks about, which has some simple steps to set up CDC pipeline to get all of the data from YSQL, Yugabyte SQL to Kafka topic. So these are the steps that I have run already just to save some time. So let us go over those steps, right? We set up some environment variables needed, and then we have a script. So I just go to the node wherein the Yugabyte is running, open the shell, and then use that script to create some tables that we will be using in the demo. In this case, orders, products, review, and users. And then in the next step, what I have done is I just created a change data stream wherein we specify this all option as discussed to say that we are interested in streaming the before image as well. And then I have just started the Docker containers and then deployed the source connector using the stream ID that we have created earlier, and followed by deploying the sync connector. And after this, we can optionally open a Postgres terminal. So in this example, Postgres is the sink. We can look how records look like there. So we have also scripts to perform some write operations into these inserts into these tables that we have created. Let us say after running these, I have 5 rows in each of these tables. And if we go to the Confluent page, and then basically what we are trying to do here is we want to see how the change records look like in the Kafka topics, right? So let us go to the topics. And if we see, there are 4 different topics created for the 4 tables that we have created, right? Now, if we go to one of the topics, let us say the topic associated with the orders table, right? And if we go to the messages section and go to offset 0, we see all of the 5 records here corresponding to the 5 inserts. And if we expand one of the CDC record just to see how it looks like, we see the before, after section and all of the columns that are populated along with the associated data. So now we have seen how it looks like, how the Kafka records in Kafka topic looks like. So now let us say I'm dynamically creating a table in the Yugabyte database against which I have created the change stream. So let us say I'm adding a table dynamically now, and let us do a couple of write operations. So first I inserted a row, and then subsequently I'm updating the same row here. So in this case, if we go and now have a look at the topics, Kafka topics in the Confluent page, we see that there is a new topic created for the new table, orders 2 table that we have created. And if we go to the message section with the offset, by going to offset 0, we see both of the records shown up already, right? Even though we created it dynamically. So the changes associated with this are also streamed. And if you see the first one, insert, the before section is null, and the after section has all of the information about the inserted row 1, 2, 3. Now, if we also go to the update, we have the before section populated with the value 1, 2, 3, which is the before image. And then after image has the value 1 incremented by 1 with the values 1, 3, 3, showing the current image post update. Right. So now let us see the same, how it behaves, how CDC behaves with alter. So I'm now modifying the schema by adding a new column. Let us say I'm adding a column value 3 here, and then subsequently updating the newly added column. I'm setting the value of the newly added column to 9, right? Value 3 equal to 9. With this done, let us go again to the Kafka topic. And then see what do we have in the messages section, right? So if you see, there is a new record that got populated associated with the update. If you see here 133, and then if you also see, I just paused here, you also see value 3 being null here, right? So we are using the schema associated at this point in time. We just added a new column, value 3, and in the before section we have value 3 also showing up with the value being null, and in the after we again have value 3 also showing up with the value with the set value as 9.
R.K.N,
Right?
One question is, let's say if you look at line 41 and 42,
Yeah.
why is the name of the column repeated twice?
Oh. I just need to go back and see.
No worries. We should take that offline and maybe follow up.
Sure. Yeah. I'll note this down and then look into it. Yeah. Thanks for pointing it out.
Sure.
Yeah. So now we have the update record now shown up here. Now, finally, let us see the behavior with tablet split. So what I wanted to do is I just want to split the tablet manually. So before that, we should know what is the exact tablet ID, right? We have a command to do that. And then for doing that, we should, what I do is I just go to the UI associated with the T server, and then find out the orders to table that we newly added, and then pick up the tablet ID from the UI. And then I'll be supplying that. So before doing a tablet split, I'm just doing a tablet compaction followed by a tablet split. So to the tablet split, I supply the same tablet ID, and with that, the tablet would be split now. So post tablet split, we can also see in the Docker logs. So if we go to Kafka Connect and then Kafka Connect logs and then see, we will also see a log saying that, the tablet split has occurred, encountered a tablet split on so-and-so tablet. So that's the same tablet ID which we have used for splitting the tablet manually, right? After this, so now we have two tablets here, and after post this tablet split, if we go and do write operations again. So let us say I'm inserting a new row again, just continuing on the previous table that we earlier had, right? So I'm just inserting a row and then updating the newly inserted row by setting the value 3 column to 9. I just inserted 2, 3, 4, 5 and updated value 3 column to 11. Now, if we just go to the Confluent page again and have a look at the CDC records under the message section by jumping to the offset 0, we will see a couple of new records here again, right? The first record is about insert that we have done. So 2, 3, 4, 5. And of course, before will be null because it is an insert. And next, if we have a look at the update record, right? It will have the before image as 2, 3, 4, 5. And the after section would have 2, 3, 4, 11. And that's what we have set for the value 3 column. So yeah, that's pretty much it. I try to keep it as simple as possible so that we can relate it better. But of course, in the real time, it is much more complicated. Yeah,
I think the examples are super helpful, Ken. Thanks for also recording the demo upfront. It's made it more efficient. I did mean to ask you if you could shed some light on some of the future work that's coming in the general area of change data capture.
Right. So there is pretty much a lot of work going on on top of CDC. So if you take the features, these features itself, for example, right? So for example, before image. So today, before image, CDC in general does not support, when primary key is modified, we do not allow changes of those the corresponding changes to be streamed across, and it doesn't work. CDC doesn't work with primary key changes. That's one thing we are looking into, and then that's there in the pipeline that we want to take care of.
This is referring to if somebody updates the primary key, you do an update where the primary key column is modified. So essentially, that's like probably we could consider showing it as a delete of an old record and
exactly and insert. Right.
So, right. Okay.
And then we are also looking into the performance section. So basically, if you take before image, for example, right? So a side effect of before image is, it impacts reads also to some extent, right? So we want to handle that. We do not want any performance impact because of enabling, features associated with CDC. So what we are also looking into is keeping the main cluster intact. We want to put all of the changes into another another cluster kind of thing, right? It could be a kind of read replica or whatever we call it, right? So use that for CDC rather than disturbing the main cluster. And then we have many limitations on the before image itself, right? So for example, if after starting a transaction, within a transaction, for example, I modify a row. So I inserted within a transaction and modified it a couple of times. So the before image always refers to the image prior to the transaction beginning. So within the transaction beginning, whatever writes had happened, if I want to stream the before image associated with the writes that had happened, if a row is touched upon more than once, so we have the previous row version also part of the same transaction, right?
Yeah, also
So
that seems like a little bit of an advanced ask. It seems like for transactional model, it's okay to show the after image of the transaction and before, and not necessarily the intermediate, but maybe some databases do it. I don't know. I think we should mention one of the other areas where if you have two tables you are subscribing from, or if you care about inter-row atomicity on the, I think there's some work happening to make sure that.
right.
Go ahead.
Yeah, I was about to talk about that. So we are working on the consistency as well. So what we are doing is we are streaming per tablet today, right? And so on the other end, on the consumer end, if he wants to consume all of the events at the transaction layer, so first a particular transaction has occurred, then that particular ordering. So basically, to put it short, if you want to ensure consistency, that's not that cannot be achieved today directly by just streaming at the tablet level. So we ensure in-order delivery within a tablet. So per tablet we ensure in-order delivery, but if you want to do it at a table level across all of the transactions, so if you want to ensure consistency, that's not there yet today. So we are working on that, and work is in progress on that front.
Yeah, so in future you will be able to gather all changes on behalf of a single transaction, which may be multiple rows of living in different tablets of a table. They could be, rows in two different tables. If you want to kind of atomically gather all the changes at a per transaction boundary, we're working on some of those enhancements to CDC.
Right.
Wonderful. Anything else, R.K.N?
No, that's all I have.
Yeah, we are a little over time as well. So again, I wanted to thank everyone that joined today for the talk. See us on another episode of the Friday Tech Talk next Friday. And thank you, R.K.N, for a wonderful talk. And over to you to wrap up.
Yeah, thanks everyone for attending the talk, and also thanks Kannan for giving this opportunity to present this particular topic. Yeah, that's all. Thank you everyone. Bye.
All right. See you folks. See you next time. Thank you.